the second part of lesson 8.8. We're going to start by letting z equal 1 minus I. In order to find the powers of z, we're first going to convert it to polar form. Remember, from the first part of the video and from 8.7, to convert to polar form, we start off by setting r squared equal to a squared plus b squared. Now, if we have 1 minus I, b is just negative 1. Remember, we don't use I in this equation at all. If we have r squared equals 1 plus 1, that would be 2. Taking the square root of each side, r technically could equal plus or minus the square root of 2. We're going to keep this part of our answer exact, and then we'll approximate it to graph down below. The second thing we need to do is find our theta. If we set tan theta equal to b over a, oops, that's an equal sign. Tan theta equal to b over a, that's negative 1 over 1, which would just equal negative 1. On the unit circle, tangent equals negative 1 in 2 locations. That would be at either 135 or 315. Which one of those measures would make 1 minus I in the correct quadrant? Well, 1 minus I would put us down in quadrant 4. That means our rotation should be 315. Therefore, z in polar form would be square root 2, and then because it's polar for complex, we have to do that CIS, 315 degrees. So we're going to start with that. I just had to make the screen pretty big for this second step. It says for part B, find z to the negative 1, z to the 0, z to the 1, all the way up to z to the 8th. Oh, Mrs. Fry, what were you thinking? This will actually be pretty cool when we're done. You're going to have to write fairly small in this chart. I thought for whatever reason I made it big enough, but even when I wrote it out, I had to write pretty tiny to get everything to fit. Hopefully you'll be able to get that to fit as well. All right, we're going to apply Dumov's theorem from 8.8 part 1. Remember, where your exponent is what you raise the r value to, and then you multiply it to the theta. So here we go. If z by itself is square root 2, CIS 315. That's going to be our template for all of these exponents down below. If we have z to the negative 1, that means we have to take square root 2 to the negative 1, CIS, negative 1 times 315. Well, square root 2 to the negative 1 power, that's going to be 1 over, oops, sorry, hang on. So that equals right there. This becomes 1 over square root 2, and then CIS, negative 315. A couple of things here. We have to rationalize the denominator, and our r value has to be between 0 and 360. So from here, let's go ahead and convert 1 over square root 2 by rationalizing the denominator, and you get square root 2 over 2, CIS. If we're at negative 315, we're going to have to add 360 to that, and that would put us at 45 degrees. That's our answer for z to the negative 1 in polar form. Let's try the next one. Z to the 0 power. This one will be a little easier because of the exponent 0. That means we're going to take square root 2 to the 0 power, CIS, 0 times 315. What makes this easy is that anything to the 0 power equals 1. CIS, 0 times 315 is just 0 degrees. And that's our answer for z to the 0 power. The next one that's pretty easy is just plain z. That's our original z value. That's automatically square root 2, CIS 315. From here, it's where things get a little bit trickier. In order to get z squared, we have to take the square root of 2 and square it, CIS, 2 times 315. If you type that into your calculator, square root of 2 squared just equals plain 2. It's like the root and the power cancel each other out for this one. And then we have CIS, 2 times 315 puts us at 630. But that's bigger than 360. In order to get rid of that, I'm just going to subtract 360 until I find a coterminal answer within our range. 630 minus 360 would give us 2 CIS and then we're at 270. And there's your answer for z squared. Z to the third, again, this is where it gets tricky because we want our answer to be exact. So watch what I do here specifically on z to the third. If we take square root 2 cubed, CIS, 3 times 315, unfortunately plugging that into your calculator gives you a decimal. We want to keep this exact. So what I'm going to do is I'm going to take my answer from up above and multiply it by another square root 2. And that would be taking it to the third power. Our answer from the squared power times the square root of 2. CIS, if I multiply 3 times 315, we get 945 degrees. So what we end up having here is 2 square root 2 CIS. If we subtract 360, we're going to have to subtract it twice in order to get an answer that's between 0 and 360. And we get 225. So what I'm going to do now is just kind of show you quicker how to get through these values. This is the process behind it, but I want to save us some time to get to that graphing. For z to the fourth power, if we take square root 2 to the fourth power, CIS, 4 times 315, anytime you take a square root to an even exponent, you're going to get an exact answer. So you actually can plug that one into your calculator. It's kind of nice. The odd ones are always going to have a square root of 2 in the answer, like it did up above for z to the third. At any rate, square root 2 to the fourth power is 4. CIS, and then 1260 is obviously greater than 360. If you subtract 360 multiple times, you get it all the way down to 180 degrees. I've put z to the fifth and z to the sixth power on here. Z to the fifth, because it's odd, I just take my last answer for r and multiply it by square root 2. Therefore, square root 2 to the fifth power would be 4 times the square root of 2. CIS, 5 times 315 is 1575. You have to subtract 360 until you get all the way down to 135. Z to the sixth, take square root 2 to the sixth power, you get 8. 6 times 315 is 1,890 degrees. Once you subtract 360 a whole bunch of times, you can simplify this to 8 CIS 90. For our final two powers using de Moivre's theorem, square root 2 to the seventh power means we take our previous r value of 8 and multiply it by square root 2, giving us 8 square root 2. CIS 7 times 315 is 2,205 degrees. You subtract 360, like I said, a whole bunch of times until you get an answer that's greater than or equal to 0, less than 360, and we get down to 45 degrees. The last one's kind of tricky. If we have square root 2 to the eighth power, that equals 16. I mean, remember, anything that has an even exponent, we can plug into our calculator and get an exact answer. 8 times 315 is 2,520. Now, when you subtract 360 a whole bunch of times, you actually get down to exactly 360. But remember our rules for these, it has to be less than 360. Therefore, if you subtract it one more time, you get 16 CIS 0. In the next column, we actually have to convert all of these back, to rectangular form in order for us to sketch our graph down below on that Argand diagram. If you recall the template from 8.7 to convert from polar back to rectangular complex number form, it's r times cosine theta plus times r sine theta. You're definitely going to want reference to your unit circle, so make sure that you have access to one while we go through these. All right, z to the negative 1. We're taking r times cosine theta, which is going to be square root 2 over 2 times cosine 45, plus I times square root 2 over 2 sine 45. What's interesting about this is when we look at 45 degrees, cosine and sine are both exactly square root 2 over 2. Therefore, we're multiplying square root 2 over 2 times itself. So it looks kind of strange to start us off. And when we multiply the square root of 2 times itself on top, we get 2 over 4. Plus square root of 2 times itself on the top is 2 over 4i. And that's going to simplify to 1/2 plus 1/2 I. That would be z to the negative 1 in rectangular form. That one's pretty tricky. The next two are pretty easy though, which is kind of nice. Wow, can you hear that airplane? Sorry. All right, anyway, z to the 0 power, we have 1 cis 0. To convert to rectangular form, that would be 1 cosine theta, which is 0, plus I, 1 sine theta, which is also 0. Cosine at 0 equals 1, so that's 1 times 1. I times 1 sine 0, that's just 0. So that would be 1 plus 0i. I know 0 technically cancels it out, but we want to write it in the rectangular form for a complex number. The last one that's pretty easy is plain z. That was the complex form that we had all the way at the beginning of the problem. If we have square root 2 cis 315, that just means 1 minus I, and that's from the beginning. So we don't have to recalculate it if we were already given that z value. It's the rest of them that are going to be a little bit tricky. So I'm going to go through them quicker like I did last time so that we can finish this problem up. For z squared, we had 2 cis 270. To convert that to rectangular form, 2 cosine 270 plus I times 2 sine 70 just becomes 0 minus 2i. So that one wasn't too bad either. Check out z to the third. 2 square root 2 cosine 225 plus I 2 square root 2 sine 225. On the unit circle at 225, both sine and cosine are negative square root 2 over 2. We're kind of noticing a theme here on some of these. If you multiply all of this together right here, this much of it, put that over 1, what ends up happening is that you actually get just negative 2. 2 times the square root of 2 times another square root of 2 would be 4. Over 2 would be 2, and then that negative makes it negative 2. Pause the video and try to type that in just to verify if you want to. And then we have I times the whole same thing again. 2 square root 2 times negative 2 all over 2, gesundheit. All right, is also negative 2. So that, whoa, hang on, what's happening here? So that means we have negative 2 minus 2i. That would be our number in complex form, or in rectangular form. In order for us to finish this lesson efficiently, I just want to let you know that our following answers would be like so. Z to the 4th power would be negative 4 plus 0i. Z to the 5th is negative 4 plus 4i. Z to the 6th, 0 plus 8i. Z to the 7th, 8 plus 8i. And then finally, z to the 8th, 16 plus 0i. Had we gone through the work to convert those back to rectangular, those would be the answers we get. Down below, we're going to plot all them to see what kind of shape we create. To plot these on the Argand diagram, what I did was I took z to the negative 1 all the way up to z to the 8th and just created the ordered pairs that I needed from the Argand rectangular form up above. For example, z to the negative 1 would be 1/2 comma 1/2, z squared 0 negative 2, all the way up to z to the 8th 16 comma 0. You can either write all these down just to have them as reference or recognize that those points are what we would create using the complex form for the rectangular version up above on that right-hand side. Now we want to plot all of these coordinates on our coordinate system on the right. We're almost there, everybody. We can do this. Z to the negative 1 is 1/2, 1/2. I'm going to count to the right and up 1/2 and put me right in the middle of that first square. Then I have 1, 0. Over here to the right of that. Down below, 1, negative 1. We go slightly off our graph here at 0, negative 2. So I'll just kind of drop that down below that dash mark, or below that segment. Then we go negative 2, negative 2. So again, we're a little bit off of our graph. From there, we're going to go negative 4, 0 to the left. Up negative 4, up 4. And then we go all the way up to 0, 8. Like so, over to 8, 8, that puts us over here. And then from there, I've got to count over to 16, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to go with that right there, that point to the right. Oop, I think I'm off one. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We'll go with that. Okay. Last but not least, well, this video needs to be over. Let's connect from start to finish, and what happens is we're going to form this nice smooth curve through all of these coordinates. And voila, there you have the sketch of the exponents for, or the powers for z equals 1 minus I. You'll notice I moved that last point over to the correct coordinate to make that loop happen. Wow, and there's lesson 8.8.